Howdy, I'm Josh Yang. I'm a senior electrical engineering major here at Texas A&M.
And howdy, I'm Peter Erskine. I'm also a senior electrical engineering major at Texas A&M.
Howdy, I'm Joachim. I'm a junior electrical engineering here at Texas A&M.
Our research involves using reconfigurable antennas in the phase of a wireless channel to generate a private encryption key between two users. Currently, the most common key generation methods are public key and private key. Public key methods are very computationally intensive, and private keys require the users to meet and share the same key. In our method, we use the characteristics of the wireless channel to generate keys rather than sharing an actual key wirelessly.
This project relies on the principles of multipath scattering and reciprocity. Multipath scattering means that when a signal is sent from antenna 1 to antenna 2, it doesn't just take one path to get there. Instead, it bounces and reflects off of all of its surroundings, and the sum of all the signals reach the receiver. Reciprocity means that signals sent from user A to user B looks the same as if it were sent from B to A. On this slide, simulations of the paths from antenna 1 to antenna 2 and antenna 2 to antenna 1 can be seen. As you can see, the strongest paths in this environment are the same in both cases, showing reciprocity.
First, we want to tell you a little about how the algorithm works. The encryption algorithm analyzes the phase of the received signal and uses it to generate a private encryption key. The total phase spectrum from negative 180 degrees to positive 180 degrees is divided into equal bins, and then each phase value will fall into a certain bin. The total number of bins is determined by the largest phase difference measured. Next, each bin is labeled by a binary string, and the corresponding binary string is then added to the encryption key. This is done for each frequency component until a final key is constructed.
The difference between current encryption algorithms and our algorithm is the fact that we implement an error checking method. Instead of numbering the bins sequentially, they'll be numbered with every other bin ending with a 1 or 0. The least significant digit in each bin will be called the error bit. Before the bin label is added to the key, the error bits will be compared. If they are the same, then the label gets added to the key. If not, then the algorithm rounds to the nearest bin and adds its label to the key. This method gives us a half bin room for error.
The antennas designed work at 2.48 gigahertz with a bandwidth of around 36 megahertz. This is controlled by several factors: the length and width of the patches and the location of the inset. The length determines the resonant frequency, the width determines the impedance, and the inset balances the impedance to match the transmission line. The design parameters determined can be seen on the slide in front of you. The antennas are also designed to be reconfigurable. This means that with a flip of a switch, the antenna can change its polarization by 90 degrees. This is done by using diodes as switches. Arm 1 of the antenna has diodes pointing towards the center patch, while Arm 2 has diodes pointing away from the center patch. Arm 1 will be excited with a positive bias, and Arm 2 will be excited with a negative bias. This bias is determined by the user through a graphical user interface delivered to the antenna through a microcontroller and switching circuit.
There is also an additional security measure due to the reconfigurable antennas. Different polarizations generate different keys in a multipath environment, so two users can generate two different encryption keys in the same environment.
The full system diagram can be seen on this slide. The GUI controls the antenna, which generates channel characteristics in the signal analyzer. The GUI then takes in the information received by the signal analyzer and runs the phase information through the algorithm to be displayed to the user. Next are pictures of two different experiments. The one on the left shows line-of-sight transmission, while the picture on the right is the setup with no line-of-sight transmission.
On this next slide, this table shows us that the phase statistics at different polarizations of the antennas. Each digit in the left column corresponds to the polarization of each antenna. For example, 0, 0 and 1, 1 correspond to similarly polarized antennas. As you can see, the maximum phase difference, or phase error, is much lower, and the power is much higher for similarly polarized antennas.
The GUI as seen on this slide and mentioned previously is the interface with which the user can control the antennas as well as view the channel's data graphically. The buttons in the top left control the polarizations of the two different antennas. It also shows the phase distribution over frequency plot, phase statistics, the bits per bin, the number of bits in the key, and both the keys generated based on the algorithm explained earlier.
The slide shows two sets of results. The screenshot on the left shows the experiment setup with line-of-sight transmission. As you can see, the phase distribution is very linear, which gives matching keys, but with no randomness. The screenshot on the right shows the no line of sight transmission results. This shows nonlinear distribution, but due to the low power capabilities of the antennas, reciprocity is lost. The next slide shows two screenshots taken under the same conditions, but with the antennas at different positions. As you can see, a shift in position drastically changes the key it generates, despite its linearity.
In conclusion, we determined that the line of sight tests work under current experiment limitations, and that this key generation algorithm is feasible. The line of sight tests give us linear phase distributions, but with consistent keys and higher power. It also shows that at two different positions, two different keys will be generated. Now, real-world phase distributions in rich scattering environments will not be linear, but under our current setup, we could not increase the power to generate the reciprocity needed in this algorithm.
For further study, power needs to be increased with a richer scattering environment to simulate real-world applications. Also, time domain analysis of signals can be used for more commercial applications rather than frequency domain analysis done in our experiments.
Thank you for listening to our presentation. I want to say thank you to Dr. Gregory Huff and Dr. T.A. Liu. If you have any further questions, please contact Dr. Gregory Huff at Texas A&M.